All right. So that should be it for Chapter 11. In your Chapter 11 homework, there's 1 or 2 questions about phase diagrams. You should have seen phase diagrams last semester. But if you haven't, come by my office. We'll go over them real quick. They're not terribly tricky. It's mostly being able to read a graph. So, any questions on the fascinating material of Chapter 11? All right, in that case, let's get started with Chapter 12, which is where we put everything we know from Chapter 11 into practice. So solutions. Let's see if I can. By the end of the semester, this will be working perfectly, hopefully. All right, so types of solutions. So we just looked at all different types of intermolecular forces. So intermolecular forces help tell us what is going to dissolve with each other and what 2 things are going to be not miscible. So most chemical reactions that we're going to look at in here occur between either an ion or a molecule dissolved in a solvent, where the solvent could be water, could be carbon tetrachloride, could be a variety of things. But we're going to look at the interaction between the thing being dissolved and the thing dissolving it. So as a reminder, we talked about the fact that solution way back in 108, like the very first lecture probably, that a solution is a homogeneous mixture of 2 or more substances all in the same phase, right? So a homogeneous, it would be like putting sugar in your coffee, right? You've dissolved sugar in coffee, and it's all stirred up. You can't tell where the sugar is compared to the coffee molecules. It's all homogeneous. So then the solution is made up of 2 parts. We have the solvent and the solute, where the solvent is the molecules in the larger amount. And the solute are going to be the molecules in the smaller amount. Apparently I need to get some new pens. They're all kind of drying out on me. All right, so the solvent dissolves the solute. So if you're thinking about all the Kool-Aid that you drank over break, everybody, made your big pitchers of red fruit punch Kool-Aid, right? I mean, I did. That's what I did all break. Right, the solute would have to be the Kool-Aid mix, right? Because you have your big pitcher of water and you're putting the mix into the water, right? So the water is going to be the solvent. The solute is your Kool-Aid mix that you're putting into it. Unless you're the crazy kid who wants to make a saturated solution. Where a saturated solution contains the maximum amount of solute that can be dissolved by the solvent. Right, so there's that magic point when you're adding Kool-Aid mixture to, or Gatorade mix, whatever powder drink you're making, right, where it's all going to solution real nicely, and then you start adding a little bit too much, and then either it forms a sludge at the bottom, or it gets kind of crunchy as you're drinking it, right, which means you are now at the point that's saturated. You've put in as much mix as that water can hold, right? What would be one way to get more into solution? You can heat it up, right? So this saturated solution is going to be temperature dependent. Right? Because if you got hot, you could make more space for those Kool-Aid molecules. because the water is going to have more space between each one. So saturated solutions are going to be temperature dependent. We will get to how to calculate all these things. Today's going to be kind of some definitions and just kind of big picture stuff. So let's take a look at what's going on in solution, the molecular view of this solution process. There we go. So, just like we just spent a day talking about, there are intermolecular attractions that are going to hold together your liquids and solids. When you go through the process of adding a solute to a pure solvent, you're going to end up changing those intermolecular attractions, right? Because before it was just all water interacting with water. Now you're going to be concerned with water interacting with water, Kool-Aid interacting with Kool-Aid, and the water interacting with the Kool-Aid. So before we just had one type of force. Now we're going to look at 3 different types of interactions. So before, we just had solvent-solvent. We just had the water interacting with the water. You've now added your Kool-Aid mix. So now you have to be concerned with how the Kool-Aid interacts with itself, the Kool-Aid interacting with the water, and the water interacting with the water. So you have 3 different types of intermolecular forces going on at once. And so we're going to, in this chapter, look at the 3 steps to dissolving something in solution. So if you can imagine, I'm a terrible artist, so that yours probably will look better than mine. So let's imagine we have a beaker with, I'm going to do molecules of water that look like circles. There we go. There's obviously going to be a lot more circles in there, right? So here's my just plain water by itself. I'm now going to add to it my solvent or solute of some sort. So for the solute to be able to be dissolved in my pure water, you're going to have to push those pure water molecules apart. Right? You need to make space for them. So the first thing that happens is the solvent molecules have to be pushed apart in some way. You have to make space. The second thing that's going to happen is the solute molecules have to be separated. Right? Because you're putting them all in together as like one big lump, and if you don't stir it, all the solutes end up, if you imagine a Kool-Aid mixer, you don't mix it, you put like one big chunk of crunchy red crystally stuff in one part of the pitcher. And so we're going to be able to separate them and then put them together. We'd end up with something like this, where you still have your blue circles, but now you have your green circles mixed in there with it. So that the green is still interacting with the green, the blue is still interacting with the blue, but now we have green and blue interacting with each other. So why we care about this, besides you want to make the perfect tasting Kool-Aid, is solution mixing affects freezing point depression, and boiling point elevation. So these are the labs you're going to do actually next week in your 109 lab. You're going to be looking at how does making a solution compared to a pure liquid change the depression of the freezing point or the elevation of the boiling point. So you'll see it in action. Good so far? Pretty excited? Yeah, I can tell, pretty excited. You know, because you'll have to think about this. This will be your thought experiment next time you make pasta. If you're adding salt to your water, water normally boils at what? 100-ish? So if you add salt to it, you've now raised the boiling point. So water's going to boil it closer to 101, 102. Maybe not that dramatic. But still, the water can get hotter before it starts to boil off. So your pasta cooks faster because the water's not actually boiling and evaporating. So if the person that adds oil, the oil is really just supposed to make the noodles slippery and not stick to each other. So 2 trains of thought about if you oil or salt your water. I'm of the oil because I always forget to stir my pasta. I always just dump it in there and walk away. So if I put oil in there, I don't have to stir it because otherwise you get that big clump of sticky pasta that's like cooked on the outside and like raw on the inside. And so you probably don't want to come over to dinner at my house. If I'm serving pasta, you probably want something else. All right, so this is a thought experiment about dissolving calcium chloride into water. So first, let's think about calcium chloride. Is that going to be a polar or non-polar molecule? Should be on the polar side. So polar, it's actually ionic, right? Which should be given away by my sentence right here. Right, so calcium chloride is going to be an ionic molecule, which means probably more appropriately written like that, right? 1 calcium plus 2 and 2 chloride ions. So what happens to the concentration of calcium and chloride when we add it to water? Let me finish my sentence there. All right, so in your original solution, was there any calcium chloride? There shouldn't be, right? You just have pure water. So if I add calcium chloride to it, what will happen to the ionic concentrations compared to 0? It should only increase, right? There's no way to make it less than 0. True, that's a true fact of science. There is no molarities or concentrations less than 0. We're warming up. Right, we would see those increase, those concentrations have to increase. What if we keep adding some calcium chloride as its solid form? What will keep happening to these concentrations? Right? They keep increasing until we get to a point that no more dissolves. Right? Because we could think about it in terms of that. What do these little double arrows mean? Equilibrium, right? So we are dissolving calcium chloride to make calcium ions and chloride ions. We can keep adding the solid until we get to a point where no more ions can be made, and you start seeing the solid just stay at the bottom of the solution, which is this point. A saturated solution, the maximum amount of solute has been dissolved. So now we're at equilibrium. We're actually at a point where you are dissolving the solid as fast as the solid is being remade. If you can think about that, that's pretty crazy. All right, so as fast as that, for every one calcium chloride molecule that breaks into its three ions are reforming the original solid, which is how you end up with solid left at the bottom of your solution. And solubility is going to be the measure of how many molecules, in this case calcium chloride, can be dissolved before we reach this point where no more can be dissolved. So we're working up to that. We're working at some solubility calculations. Good so far? Good. Okay. Let's do one or two other things about review, and then we'll start moving on to some new stuff. All right, so for example, we just want to look at the exciting game show of will they dissolve? I imagine this would be like on Saturday Night Live. Will they dissolve? Given two compounds, will you make a solution? All right, so let's say my solvent is the CCl4 carbon tetrachloride. First question, is that going to be a polar or non-polar compound? Should be non-polar, right? Because if I was going to draw it out, yeah, it's one too many dots. Okay. So if I draw it out right, there is no dipole moment. All four chlorines are pulling in equal and opposite directions. There's no dipole moment. Does that make it nonpolar? What if I say I want to dissolve, is CH4 going to be polar or nonpolar? Nonpolar for the same reason. If I draw this, right, there's no dipole moment. All four hydrogens are being pulled in equal and opposite directions. So, can I dissolve CH4 into carbon tetrachloride? Yes, it dissolves. Yay! And that's pretty exciting. Yes, they are soluble. All right, let's look at the other example. All right, we just said this is going to be nonpolar. What about our old friend sodium chloride? Polar or nonpolar? All right, it's technically ionic, all the way over to ionic. So it's more appropriate to write like this. Will those two guys be miscible? No. Not soluble. Wah, wah. That's okay. That's okay. Everybody feel pretty confident about that? Confident, dipole, polar, nonpolar, like, dissolves like. I'm taking silence as a yes. Perfect. I understand I'm pretty intimidating, pretty scary. People don't like to answer questions in here. You'll find I'm pretty friendly. I don't yell or anything. I'll probably make fun of you if it's a really stupid question. But it'll be in fun. It'll be because I like you. I'm making fun of you, not because I'm mean. All right, so molarity. You guys all did 108, right? Molarity is moles per liter, which is our typical way of measuring solubility, right? How many moles dissolved in how many liters. But for the next few chapters, we also need to take a look at some other crazy ways of measuring how much solute is in how much solvent. So one of the first ones is going to be molality. So molarity with the R has the big M, which is moles per liter. Molality with the L, bless you, is a small m. So as you're reading questions either in the textbook or online, pay attention as asking for the molarity with the big M or the molality with the little m. Because molality is looking for moles per kilogram. So mole solute per kilogram of solvent. And so molality is technically a more accurate measurement than molarity. Right, so if you imagine you're in the chemistry lab and I ask you to make a 2 molar solution, right? You measure out your solid and then you just fill the liquid up to the line of those volumetric flasks. Do you have any idea exactly how much water you added? Not really, you added to the line, and that's considered fine for molarity. In molality, you know the exact mass, moles, of the solute and the exact mass of the solvent added. So it's considered a more accurate way of figuring out what's in your solution. So if you have a calculator, now would be a great time to fish it out of your bag, book bag. So we're going to do a few calculations here to kind of wrap up today. And give everybody a second to find it. So let's go ahead and work on this first. This will be the warm-up practice example. So I have a solution of potassium chromate that I found in the lab, and I have no idea exactly what the concentration is. But I know that the person who made it put 38.3 grams. Oh, that's a typo. 94.0. 38.3 grams potassium chromate into a kilogram of water. I don't know why I would know that and not know the molality, but just live in my imaginary example world. So how would I go about figuring out the molality, which again is moles solute, kilograms solvent. So you know the kilograms of solvent, right, because that's given in the problem. How do I go about figuring out the moles of solute? Right, so I've given you this little tidbit of information. Right, we know how many grams we started off with. How do I go about using that molecular weight? Do I put the 194 on top or on the bottom of my fraction? Right, okay. So that should turn out to be, let me find my calculator. How many significant figures do I get? 3, right? And the 3 is coming from over here. I have only 3. So that should be 0.197. Everybody double check me on my math. That look good? Okay. So then, and we just need to divide. Good. Everybody feel good and warmed up? Everybody remember how to use your calculator? Excellent. Excellent. We're going to be using it a lot this semester, so it's not solar powered. Make sure you get batteries for yours because it's going to be in high usage this semester. Lots and lots. How many people had lab yesterday? Anybody? A few people? Yeah, you guys already started warming up your calculator. We're working our way up to natural logs, base 10 logs, e's. Those I think are going to be all the things we're going to use. Oh, we are going to use some cube roots. Cube roots. If you don't know where the cube root button is on your calculator, you got a few weeks to get there. Cubic roots. We're going to use quadratic equations. Quadratic equations. We're going to solve those all out. Yay! And then I'll show you a shortcut so you don't have to use a quadratic equation every time. Equally. Yay! Okay. This is my favorite bunch of chapters. Like I like 108. But I love 109. And so you guys are in luck. Super luck. All right, let's do the other example problem. This one is, of course, trickier because it's always my second example problem. Number 2 is always more complicated. So so let's say I want to calculate the molality of a 1 liter sucrose solution that I know has the molarity, right, big M, molarity, of 1.22. So this is going to require 4 steps. 4 steps. So the first thing we need to figure out actually, the first step is just going to be writing down all the things we're going to assume and know. All right, so we have we have 1.22, I can do it like that, moles of sucrose per 1 liter. Right, that's one thing we know from this problem. Do we know how many kilograms of solvent? Did I give you any information about that? No, I told you liters of solvent. But solvent includes both the water and the solid, right? Because if you're imagining your volumetric flask, some of the space in that 1 liter is taken up by that solid. So we're going to have to extract the solid from the water using math, not actual science, using math, and then figure out how much actual water we put in there. All right. Let's see if I can scoot this all up so we can all see it all at the same time. Okay, so now we're on to step 2. Actually, let's do mass of water. First thing we want to do is determine the mass of the water. We'll do sugar second. Determine the mass of the water in the solution. All right, so let's think our way through what do you know about this solution that can get us started? We don't know moles of water. We know moles of sugar. Yeah. We know the density, and if I know the density, what's the other, if density is in grams per milliliter, what's the other thing I know about milliliters in this problem? Yeah, you have a liter of it, which I'm going to go ahead and convert to milliliters. All right, so I know for sure I have 1,000 milliliters of solution. And I know the density of it. So the last thing I need to do for this part of the problem is the solvent part of it has to be in kilograms. So I need to get out of grams. So luckily for you, I made the math super easy on that. All right, so far we know that. So we know the whole thing altogether weighs 1.12 kilograms. Now I need to figure out how much just water is in there. So I guess we'll make this 2 kilograms. Call it 2A and 2B. So I know the whole solution weighs 1.12 kilograms. All right, and the solution is made up of water and sugar, sucrose. So if I don't know the moles of water, I can't figure out how much just water is in there. I do know how many moles of sugar is in there. So for moles of sugar, I can get the grams of sugar using, everyone's screaming at once, I can't hear you, molar mass. Yes, using molar mass. Good. So we know we have 1.22 using the molar mass of that, which was given in the problem over here, 342.3 grams per 1 mole. Again, convert that to kilograms. I know that in my solution I have 0.418 kilograms of sucrose. So I know the whole thing is 1.22 kilograms. The sucrose portion of it is 0.4. How do I get the water by itself? I do a subtraction. Good. I haven't made any math errors yet. I usually make one per class, so far I'm doing pretty good. All right, so now we are ready for step 4, which is actually figuring out the molality. So molality is moles, in this case of sucrose, which we have right up here. And we just figured out how many kilograms of water. So let's see what that turns out to be. 1.22. There, we see how to work through those. That is by far the most complicated problem you can have about molality. So if you know how to work through this kind of problem for molality, you can do all the other ones. Pretty much they're either going to be like the first example, where they've given you all the information and you just have to do the division, or it's going to be really a conversion problem, converting molarity to molality. Questions on this one? All right, let's do one more thing for class today. Let's do mole fractions, because everybody loves fractions. Fractions are the best. Or if there's quadratic equations. Fractions come in slightly higher, only because you use them more. All right, so mole fractions is a way of determining how much of each type of component is in a mixture. So this is our fancy math equation to figure out mole fraction. So let's say I had a mixture of A, B, C, all mixed up together. Some of it's water, some of it's sugar, some of it's milk. I've made coffee, something like that, right? I've made coffee in some way. And I want to figure out the mole fraction of sugar in my coffee. Because I'm real bored in my office. I'm like, you know what would be fun? Let's figure out how much sugar is in here. I don't actually do that. Often. Sometimes. It's just a funny thing to do. So, a mole fraction of just component A, which is symbolized as this. So mole fraction of A has the symbol big X, little a, where big X means mole fraction. I don't know who came up with that. Big X means mole fraction. It's going to be the moles of A divided by all the moles. Right? Because if you think of a fraction, let's say in here I want to figure out fraction of people wearing a coat. Right? I would find out how many people are in here, count up how many people are wearing a coat. Coat divided by total is the people fraction of coat wearers. So the same thing for mole fraction. It's going to be the moles of, in this case, A, divided by all the moles. Right, so using it as English rather than mathese. So let's do one more problem today. using mole fractions. Should be a nice, easy one to kind of finish this up with. So I've given you a lot of information in this problem. Some of it may be deceiving and not useful. I'm going to tell you ahead of time. There's some information there that's totally not useful. True, but not useful. So let's say I have a solution that I know contains 1 mole of ethanol and 9 moles of water. I want to find out mole fraction ethanol. So using our very complicated math that we learned on the previous page, how many moles of ethanol are in my solution? 1. What is the total number of moles? Woo, you guys are on it. Good. I feel good about your fraction use. All right, what if I wanted to figure out the fraction of water, mole fraction of water? What do you know fractions have to add to? 1. All fractions add to 1 as long as you have all the fractions. They all combine to make 1. So you could either do this, which is absolutely correct. Right? Perfectly reasonable, very true. Or that is also true, right? All the mole fractions have to add to 1. So if you know this, did I throw into a tizzy? No. Good. Fraction's pretty stable. All right, in that case, we'll finish up the rest of Chapter 12 Friday. You have your Mastering Chemistry due Friday night. It really only covers Chapter 11. So if you have a question about Chapter 11, let's work it out before the homework is due Friday night. And I will see you Friday.